Making sure that our applications don't use more memory than we think that they should is sometimes one of the more difficult aspects of writing good Haskell code. A very common scenario in which we get more memory usage than expected is when we have unevaluated thunks in long-lived application data. In today's episode of the Unfolder, we're going to take a look at how these arise and how we can use the NoThunks library to find these problems and avoid them once and for all.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and to discuss them.
Right, so I want to start with sort of a motivating example. Suppose that we are dealing with maybe a web server, maybe it's a backend server for a game or some sort of user system, doesn't really matter what it does, but the server is tracking some information about our users. And so our application state is going to be in MVar. So this is like a global variable that the entire state application has access to, which is going to contain a map from users to user info. And we're going to keep things simple, and we're going to say user is simply a name, right? The name of the user, text. And user info for now is going to be a time, and that time is going to record when the user was last active. Mm-hmm. And we want control concurrent MVar for the MVars. All right, good. Mm-hmm. This is our application state.
Yeah.
And so we need a way to mark a user active, right? Maybe the front end every so often pings the back end saying, hey, this user is active. So that gets the application state, the user who is now active. And what we're going to do is we're going to modify that MVar. We get the existing state. We just get the current time. And then we update the map. And for this new user, we just return the current time as the new state for that user, right? This user is now active. Mm-hmm. And to simulate sort of a workload, I'm going to paste in a very simple function here, which is going to do exactly that. So what this function does is it makes a new MVar, which has the empty map. So this is our initial application state, right? There's no users. Mm. And then we have a few example users, John, Mary, and Bill, and we just cycle through them over and over and over, right? So cycle takes the list and just repeats it. So this is John, Mary, Bill, and so forth. And just to take the first 20,000 of these. Then we mark that user active, and then we perform a garbage collecting. And the garbage collection is just this modeling that some time has passed, the garbage collecting gets a chance to kick in and remove some garbage. All right, and so our main application is simply a call to simulate workload.
It looks a little bit suspicious, but I guess we'll get to that.
It looks suspicious. Okay, well, let's see. So it looks suspicious. Let's figure out how suspicious it really is. So we're going to run this application. And maybe we get some profiling information because we are interested in memory usage, right? Mm-hmm. And we're going to use the event log for this. And let's also ask for some statistics to know what's happening. So we can run this application. It runs for a bit, and then once it's done, it spits out some statistics. And once it does, give it a second. We said that the maximum residency of this program was 3 megabytes, right? So that's already an indication that something is probably not right. Like, why would it use 3 megabytes? But it doesn't tell the whole story. So let's take a look at the profile. So this has generated an event log, this guy here.
I mean, yeah, perhaps we should, for people who have not done this so often, say like maximum residency is like the line that you generally want to look for in these kind of reports because it indicates sort of the highest memory use.
Exactly.
That has been reached throughout the run of the program, right?
Yeah, how much memory at any point in time did the program use? Yeah, not the total amount that was allocated and freed again, but just the high level.
Yeah. So in particular, if you scroll up again quickly, sort of like a common pitfall is a little bit that people are looking at like the bytes allocator, right? The first line. I mean, that is basically, that's often very high, right? Because in a functional language, you're often allocating and immediately freeing again, and everything gets added to that total. So everything that is allocated is listed there, but that's not necessarily bad.
Yeah, exactly. Yeah. Now, of course, 3 megabytes doesn't tell us necessarily that it's a leak. Maybe our program just needs 3 megabytes, but let's just see what the profile looks like. So we can turn this profile into something that we can actually look at using event log to HTML. So we just run that on the event log. And if we take a look, this has generated this event.log.html file here, which we can open up, and it gives us a bunch of different tabs. But the one that we're more interested in here is this graph here. And this is a graph of memory usage over time. And as you can see, it's like going up and up and up and up and up and up and up. Right.
Yeah.
So I often call this a triangle of death. Right. If you see it, this shape, almost certainly you have a memory leak, right? Because you're allocating more and more memory and you're not freeing it.
And it's classified here by type because Etsko used the HY flag. I'll never understand why Y means type, but there are different ways to classify the heap profile as well. But and here you can see, I think that map is among the top, the topmost data type that is.
And that is indeed a clue, right? So why is this happening? Well, like Anders said, the profile is telling us we have a map at the top there, right? So, and that's because when we are updating our MVar, we're not actually evaluating this, right? The MVar has a thunk in there, and all we're doing is replacing this thunk by a new thunk. It says it has a new call to a map.insert, but we're never looking at these maps, so we're never enforcing them. Right, so all we're doing is building up a larger and larger and larger expression of the form map.insert apply to map.insert apply to blah blah blah, eventually apply to the empty map. Right, so one way to fix this would be to make sure that every time we update the MVar, we force this map. Right now, if I run my code again, it will see that it will run much faster. And if we look at the same line again, we see that it's only.
I think you scrolled up too far.
I scrolled up too far. Yeah, sorry. Yeah, that's right there, yeah. Only uses 40K. And if we look at the profile again, of course, I have to regenerate it and then reload it. We see that it's now perfectly flat.
And also that it's always normalized in height. So, I mean, the fact that it is still looking very high, but if you look at the actual numbers on the left, they are much lower now.
Yeah, this was like 3 megabytes, now it's 2.6K. Yeah, exactly. All right, cool. Okay. All right. Now, I would argue that this, what we just did, change the code and insert this bang here, actually is a bad solution. It's what I would consider an anti-pattern. And the reason is that you have to remember to do this absolutely everywhere that you update this MVar, right? If this MVar is throughout your application code, one forgotten bang somewhere, and you're back into trouble, right? What we should do instead is make a new kind of MVar, a new type that always ensures that its contents is in wicked normal form. It's always evaluated, right? So we can very easily do that. So we could make our own MVar type, and what we're going to do is we're just going to wrap a regular MVar from the libraries. And now all new does is wrap the original. But the critical thing is that when we're updating an MVar, we make sure that the value is in wicked normal form. Actually, we could also do that in new here because we have a value here as well. But it's less critical, right? The more critical one is the one where we're updating. So we're going to focus on that one. So the only function we need is modify MVar underscore. So it takes an MVar, a function to update the value, and we need to apply this function. And so we're going to use modify MVar on the original one. But we're going to give it a new function. And what is this new function going to do? It's going to call the old function, the original function that you pass in, f, and then return the result of it. But before we return it, we stick a bang on here to make sure that this value is reduced to wicked normal form. So yes, we still need a bang to ensure that it's a wicked normal form, but now it's exactly in one place and one place only. Right, so now instead of importing from control.concur.mvar, I can control my own strict MVar. I no longer need to bang. And if we had other updates to the MVar, they would all benefit. And if I run my application again, we can see that indeed the maximum residence is low. Right? So this is a much better way to solve this problem.
Yeah, I think the general story here is perhaps worth reiterating on this, is that you should try to think about sort of the strictness and variance you want to hold for your data types. And that applies both to sort of general purpose data types like an MVar, but also to user-defined data types. And you should try to attach these invariants to your data type in such a way that you have an interface to the data type that maintains those invariants, so that when you're using the data type through that interface, you never really have to care, right?
Yeah, exactly. Yeah, that's why we like Haskell, right? Because we can express things in types, which are then verified by the type checker, and we don't need to worry about it, right? Yes, exactly. All right. So far, so good. Now let's suppose that we done all our due diligence, the server is running smoothly, but now at some point somebody decides we want to keep track of a little bit more information per user. We don't just want to keep track of the last time they were active, we also want to know how often they were active. So what we're going to do is we are going to replace the user info, which currently is just the time, with a new data type, which is going to be a record of a bunch of stuff. And for now, let's just assume that we still remember when the user was last active. And we also remember now how many visits they had. All right. So previously, we were just always overriding the value in the map. Now we can't do that anymore, right? When the user is marked active, we need to make a distinction. Was this the first visit, in which case visits should be 1 exactly, right? Or was this a subsequent visit, in which case the number of visits should be incremented by 1. Right, so let's define 2 cases for both of these scenarios. So first visit is just going to be a plain user info. And we're going to set the last active to be the current time, just like we did previously. And the number of visits is going to be 1 on the initial visit. Right, and we're also going to define a function, which is going to be used for subsequent visits, which is going to take the current info as an argument and is going to construct a new user info. And the last active is still going to be the current time. That doesn't change, but the number of visits is now 1 more than we started with. Visits info plus 1. Okay, and now instead of calling map.insert, we can call something called map.alter. And the structure of alter is a little bit different. So it's going to take a function that is used to alter the map. Then the key, I don't know why they're in opposite order, but they are, which is still the user, and then the map. And so we need to think about what this argument here is. Now, that this function here is going to be a function from maybe user info to maybe user info, as you can see here at the bottom. The input is going to be nothing if there is no entry in the map yet. The output is going to be nothing if we want to remove the entry from the map. Right, so in our case, we never want to remove the entry from the map, so we can just always return just the value. So now we either have the old info, if 1 exists, or nothing if this is the first visit. And so now we can just pattern match on those 2 cases. So we can just use the maybe function for that to do exactly what we want. Like this. All right.
Yep. That looks slightly suspicious again.
Yeah, perhaps if you are a seasoned Haskell programmer, then you should start worrying here. But it's not always so obvious, right? I mean, it's obviously like this.
I'm not saying.
So let's run this code again, and let's see what happens. And it's taken longer, which is already a worrying sign. But let's allow it to run for a bit. And once it runs, we can see, 4.5 megabytes maximum residency, not a good sign. Let's also look at the profile. So I regenerate it, and then I open it up again. And we can see that we have this beautiful triangle of death again. It's a bit more complicated looking than it was before, because we have more information in our map, but definitely not good. Now, at this point, we know that our MVar is guaranteeing that our map, our value, is in weaker normal form, right? But clearly, this is not enough, right? Apparently, there's something still not being evaluated. Some calculation is not yet happening. Now, we could start reasoning through this, but actually, in some cases, that could be rather complicated. What I want to show you is how we can use the NoThunks library to avoid all that reasoning, and it will just tell us what the problem is. So how do we do that? Well, we are going to modify our strict MVar abstraction, and we're still going to do what we did before, right? We still call the function that we want to use to update our value. We still force the result to weaker normal form. But we want to check that if the result is in weaker normal form, that this also means that there are no unexpected thunks anywhere in our value. That is what we can use the NoThunks library for. That's exactly what it does. So we can ask the NoThunks library, are there any thunks in this value here that we're not expecting? Now, for this to be possible, we need an instance for NoThunks on A. We'll talk more about that in a second, but for now, I'll just add it as a constraint. And so this, by the way, is just some additional information about the context that we're in. Doesn't really matter for us here, so we can just leave it blank.
It's just used for error messages, right?
It's just used for error messages, yeah. It just allows you to give some more information. Yeah, exactly. So, okay, so if this is going to return nothing, if there are no thunks that we weren't expecting, so that's the good case, right? So in that case, we just return x prime. But if there is a thunk, it will just return just that thunk. And in our case, we're just going to throw an exception, and we're going to say we found a thunk that we weren't expecting, and here's some information about it. Okay.
But sorry, I mean, but the call to NoThunks is costly, right?
Yes, that is true. The call to NoThunks is costly. You don't want to do this in production code. Remind me to talk a little bit about that at the very end of the episode before we wrap up.
Okay.
Yeah, but it is true. Yeah, you should definitely don't want to do this all the time. Okay. Now we're getting a type error at the moment because we insisted that we have a NoThunks instance, right? This NoThunks class, whatever that is, for A, and we don't have that for user info. Fortunately, that is very easy to fix because we can just derive it. So we can say deriving generic, and then once we have generics, we can just derive NoThunks, and our problem goes away.
Okay.
And now when we rerun our code, and we don't need profiling now, we can just run it as normal, we're going to get an exception here. And we get an exception with a backtrace. We talked about backtraces in the previous episode, but that's not all that relevant here. What's relevant today is this line here. It's telling us we found a thunk. Now it's giving us 2 bits of information. It's telling us that oh, I see that I'm skipping ahead a little bit, but it doesn't really matter. It's telling us that we have some context that's telling us where that thunk is. And it's also telling us where we created that thunk. Now, this bit of information depends on info table profiling, which was implemented by Matthew Pickering and some other people a while ago. And from the get-go, like I wrote NoThunks many years ago for a client. At the time, it was already like we knew that was going to happen, and so there was a to-do in the code base saying, "Oh, it would be very nice if we could take advantage of that information." And now, Marcin Somotilski actually has implemented this, which is really nice, right? So now he's implemented this, and so now you can actually get that information, not just what the type of the thunk is, but also where it was created, which is very, very helpful. So it's in this case, it's telling us that it happened on line 32 here, right? Okay, so it's telling us that something is wrong with this current time, and that location information is not always entirely accurate. So it's also telling us, well, we have a map in our MVar, right? Which is fine. The map is in wicked normal form. That map contains some user info. That is also fine, also wicked normal form. The user info has a field called last active, and that field has type U2C time, and that field is not okay, right? So everything in this stack here is fine except for the head of the top of the list here, the first element of the list.
So, by the way, you're saying everything is fine. I mean, so if there are multiple thunks, it's only giving you one, right?
That's true, yes. But if, for example, the map itself or the user info would not have been fine,
then it would have reported that one first.
Yes, yeah. So, for example, suppose that currently I'm using a strict map, which means that if you evaluate the map, you also evaluate all the elements in the map, right? Suppose we didn't do that. Suppose we had a lazy map instead, and we rerun the code. Then it tells us that the map is fine, but the user info is not fine. Yeah, and that's because we did force the map to wicked normal form, but there's an element in the map of type user info which is not in wicked normal form. So the thunk is here.
Yeah.
Right? Okay. By moving to a strict map, that can't happen anymore, right? Forcing the map also ensures that we force the user info in the map, so this can't happen. But of course, forcing the user info does not force the time, right? Because there's no bang here.
Yes, but it is slightly surprising that we have to, right?
It's maybe somewhat surprising, yeah. But
Because
so what it tells us,
get current time. I would have expected that to return something that is fully evaluated, but apparently it doesn't.
You would think so, yeah. But it doesn't. And so, okay, we can force it to force this wicked MVar, and now we run this again. And if we do, we see that it's still complaining about the time. And now it's telling us, okay, we have a map containing user info, containing a field last active of type UTC time, and somewhere inside there is still thunks.
Okay,
we
so
don't
it's
exactly
not
know
just
where.
returning something that isn't fully evaluated, it's returning something that is completely unevaluated.
It's returning something that is somewhere deeply inside is some computation, and forcing the time to weaken MVar does not actually force that computation to happen. Honestly, I consider this to be a bug in base, right? I mean, the fact that it returns something which is not normalized, that's, I guess, okay, but putting a bang here should force that whole thing, I think, in my opinion.
Yeah, probably. But also, to be honest, I guess this, making this part, fixing this part is not actually solving the space leak, right? Because,
that is true.
We're not building larger and larger UTC times, so even though every single UTC time is a thunk or consists of some thunks inside, is not actually contributing to the overall maximum residency.
Yes. So that is true. So when you do work with the NoThunks library, you're going to get cases like this, where you're going to get thunks in places that are sort of innocent, right? You don't care. Now, there's definitely ways that you can say and express that you don't care, and we'll see some of those ways at the end of the episode. But you have to be very careful. But we'll come back to it.
Yeah.
For now, let's just make sure that there are no unevaluated things in this time, so we don't have to worry about it anymore. So we can just call force from the deep seek library, just walk over the entire thing and run all computations that live inside there. All right, run this again, and it's still unhappy now. And this is probably the one that most seasoned Haskell programmers were expecting seeing this code, right? What's happening here, every time that we call this, we increment the number of visits, but forcing the user info does not force those visits, and so we build up a use computation that says 1 plus 1 plus 1 plus 1 plus 1 plus finally this one. And so we definitely want to force those also, so you stick a bang on there as well.
Yeah.
And now when we run this again, now we get no more exceptions, and now we run this with profiling and let this run. Then hopefully, if things go well, we should see that, yeah, indeed, this program now runs in constant space, right? 40K. I mean, just to be sure, we could actually also look at the heap profile, but it's nice and flat. All right, good. Some remarks about all this stuff. Suppose that our user info, and I'm gonna just comment out all this stuff because we're kind of done with it for a while. Suppose our user info all additional has some additional field, and this has of type some other info. Right, and some other info comes from a different library, not the library that we wrote. Now, if we now try to derive NoThunks for this new data definition of user info, we're going to get a type error because there's no NoThunks instance for some other info. Now, if we have access to this library, of course, we could add the instance, and we could maybe even, if it has a generic instance, we could even derive it. But there are also other options as well. One option is to say, well, when you check user info for thunks, I don't actually care about this field, right? Which is also something we could have done for the time, right? So we could say that actually. We can say deriving NoThunks via allow thunks in. So this is just the deriving via extension. And so we're going to say just a field name here. What did I do?
Allow thunks in, I think.
Yeah. User info. Okay. So this is just a new type from the library, which is defined specifically for new type deriving. So here you can specify a bunch of fields that you say, okay, I don't care about thunks in these fields. Now you have to be very careful doing this, right? Even if this was type int, say, you might say, well, I don't care about forcing an int, but that's not the point, right? an unevaluated int could hang on to all kinds of stuff, right?
Yeah.
It's not the size of this thing that matters, it's the size of the things that it hangs on to that matters.
Mm-hmm.
So if, for example, like for example, in the case of time, that every time we update the time is because of a call to get current time, and there is no compounding effect, right? There's no computation that builds up, then we will be justified in just not checking this field, right?
Mm-hmm.
But if you're not sure, then this is dangerous, relatively dangerous thing to do.
Yeah. Nevertheless, it's good to have, right? Because there may be some things which crucially rely on laziness, and you don't.
Absolutely.
You still want to eliminate all other thunks and leave that part alone, right?
Yeah. So there are definitely types that definitely very much depend on laziness, and an example is, for example, a finger tree, and so they will need bespoke instances for NoThunks to carefully allow for the thunks that they need, and no other ones.
Yeah.
All right. So yes. So this is one option. The other option is oops. Maybe I just say NoThunks again. Right. And so I was back complaining about some other info now. The other option is to derive our own instance for some other info, but bypassing the definition of this type completely, simply by looking at the Haskell heap. So this is another combinator offered by the library, and this is black magic, right? So it doesn't go through the types class system, it just looks at the raw Haskell heap. But you can use this if it doesn't depend on any instances available for some other info, right? So this will always work. It might not give you the answers that you want, because if some other info does have thunks in there that must be allowed, we have no way of providing special cases here, right? But if you really want this to be completely thunk free, then this is one way to do it. All right. So
and
finally,
the UTC time instance is using this, right?
That's correct. Yeah. So that's right. So there are actually two downsides to using inspect heap. One is that you get no way of of special casing, right? Like allowing for some thunks and not others. The other problem is that we get less information about exactly where the thunk is. Right? So I don't know if you remember, but we saw
that's
something
why you
like
got the ... in the context.
Yeah, exactly. Right. So we saw something like this in the in the profile here. So, and these ... indeed say there's UTC time, but after that we gave up on the class system and we looked at the heap directly and we found a thunk, but the heap does not. The heap does give us enough information to tell us that there is a thunk, but does not give us enough information to know anything about type names or field names or anything like this. Yeah, exactly.
Yeah.
All right. So finally, to conclude, let's look briefly at how you can define your own handwritten instances for this class, because it all looks a little bit magical, and it really isn't all that magical. There's a bit of magic, but not all that much magic. So suppose that we have this definition of foobar, right, which has two constructors, int and bar int. And we're going to define our own handwritten instance for foobar. Now, the NoThunks class has two methods, or three actually. One is called NoThunks, and this has a default instance, default definition, and you almost never want to override this, because here there's magic happening. Right? What this does is it looks at the Haskell heap, right, black magic, to see if this argument is a thunk, yes or no. If the argument is a thunk already, then we don't have to go looking for thunks. We found one, right? And so it doesn't do anything else. It just reports the problem. If the argument is not a thunk itself, it calls w NoThunks. So the w here stands for weaker normal form. So this is a function which, by contract, will only be called on arguments which are in weaker normal form, which means that we can actually pattern match here, right? If we try to pattern match without knowing that our argument is in weaker normal form, then we would at that point force the argument to weaker normal form, right? Which is problematic. We don't want to be forcing when we're checking for thunks.
Yeah.
But since we know it's a weaker normal form, then we can just pattern match, and in this case, maybe we want to check that both A and B are in weaker normal form, which is not all that difficult, but the library does provide a combinator for this very common case, and so we can just recursively check both of these fields. And this context just lists strings, right? So you can put any information here that you want. And for example, maybe we didn't get these field names, but maybe we think of this as A, the other as B, so we can actually put that in.
You have a quote instead of a colon.
A colon, sorry.
Line.
Yeah. Right, exactly. And so we should do the same thing also for bar here. Right? And then the final thing that you need to define is a way to actually, if we do find a thunk at this type, how do we show this type? And that depends on generics also by default. And if you have no generics, you can just say what the name of the type is.
Very nice.
And so if, for example, in your type, you wanted this to never be checked because you know by your own invariance that this could be a thunk, but one that you actually want to allow for a thunk, you can just omit checks, right? And you don't have to worry about this. Okay, so then the final thing to mention briefly is...
Yeah, we have
a question, yes.
Question. So there was a little bit of discussion about like the definition of get current time, which Pi and Travis both looked up, but I think it's kind of besides the point. We don't want to like dive too deeply into that definition. Like, I mean, but Adam had a question. Could inspect heap use IPE info to provide more context?
I think we do actually get IPE info. No, actually that's not true. I suspect it could possibly be done. I think right now it doesn't. It uses the IP info is coming from a package called where from, which is some sort of shim package on top of GG, right? But that's all Haskell land, right? Once we start inspect heap, we dive into C land and we don't get back out to Haskell land, right? So we can probably modify that code, the C code, to actually get that IP info, possibly, but it's not currently done, I think. I think that's correct, true. Yeah.
Perhaps something to think about more.
Yeah. Any other questions?
No, sorry for interrupting you. I think you still wanted to say something about this point about production code versus...
Yeah, exactly, yeah. So the way that I recommend using this library is that you CPP this check. Right, so if debug, yada, 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 right? So then what you do is when you do your testing of your application, you enable this debug flag and you compile in these checks. And in production code, you don't enable this debug flag, and so you don't compile in the checks. Now, if your tests are set up correctly, and this is usually a stateful API, right? So if you use property-based, state-based testing, right, where you are constructing minimal counterexamples when you find a problem, not only will you be checking for thunks in your tests, but even better, you will get a counterexample, which is minimal. Right? There are other ways to test for unexpected thunks, right? By setting, for example, a common technique is to set a maximum size on my heap, run my code in test mode, and if I exceed the size of the heap, then I know something went wrong, right? But that's, although it's better than nothing, it's not perfect because it means that we need to generate quite a bit of data before we exceed this limit. And what's worse, this very thing that might push us over the limit had nothing to do with the actual bug, right? So with this approach, where we check for thunks, you have your property-based tests, you get a minimal counterexample to the very moment that you introduce your very first thunk. Right? So it's a very effective way of making sure that your code never introduces thunks you weren't expecting. And so, yeah, that's how I recommend using this library. Integrate this into your property-based testing. Yeah.
Okay.
That's the last thing I wanted to say. Is there other questions?
No. Not right now.
All right.
Okay. So thanks for watching this
Sorry.
episode of the Haskell Unfolder. And if you enjoyed it, please like and subscribe, and feel free to leave any comments below.
It doesn't matter how many episodes we do.
No, we are always getting
comments.
this one wrong. Yeah, it's we would like StreamYard to make this a one-click thing rather than a multi-click thing.
Yeah, that would be so much better.
Yeah.
Anyway.
Okay. Anyway, yeah. Thanks for watching again.
We leave
leave
the
the
stream
chat
open
open
for a
for a
bit.
couple of minutes, and afterwards, questions are of course welcome in the actual comments for the video. So yeah, thank you. We'll be back in a couple of weeks. We don't exactly know yet. There might be a slightly longer delay because I'm about to move, like you can see with the boxes behind me. Okay.